That was my reaction too. Ow. I remember something. The first exam average was an 81. The second exam average was a 71. I do not want to see this trend continuing, people. Ow. High score was an 89. I went back and triple checked every single question. I took right from the text. If you look at the answer key, it even tells you which question they are. And in barely any of them did I even change wording. I tried to stick to your homework questions and pick something very similar to the questions I know I'd assigned you. I'm trying to make this as not out of left field as possible. The single thing that hurt most people is not writing testable hypotheses. If you couldn't write H null and H1, then when you did a test statistic, how did you make a decision? I'm going to reject the null hypothesis. I had somebody leave the first part of the question where it says, give me the null and alternate hypothesis blank, and then do the entire second part, and then tell me they were rejecting the null hypothesis. What hypothesis? I was a little confused at some points. I want you to look at the answer key. I want you to see if looking at the answer key makes it make any more sense. If it doesn't, y'all need to come talk to me. We get back from the holiday, we have one more chapter, 4 days of class, the last one of which is nothing but review. Only one more section to cover. Total of 2 new chapters on the final, but the final covers everything. So you'll see crap like this again. If you have questions, come bug me. I also double check my gradebook. No one at this point is guaranteed to fail this class. Every one of you can pass. I know that for sure. You might not like the grade you get passing, but you will pass. And I can tell you what you need on the final to do that. But that's assuming that the barest pass is the minimum you're aiming for. Aim higher, you'll get better. Meanwhile, I want to do more ANOVA. This model with replication is also sometimes called the full factorial model. But I like to think of it as the repetition model. So what we do is very similar. If I'm doing 2 factors, I have factors A and B. There are cases for each one. And just like on Wednesday, I get observations for each combination of factors. But this time, I observe each combination more than once. So in our example on Wednesday where we had different hotels and different drivers for Uber, different taxis, we would say, oh, well, this person took this driver to this hotel and it took this many minutes, 23 minutes and 28 seconds. But we only had one piece of data for each combination. Well, this time I want to increase that. Ideally, I'd like the same number of observations for each combination. This is called balanced data. And there are adjustments we can do when we have unbalanced data, but we'll just start with balanced for the moment. Okay. Again, I am not going to do these calculations manually. Doing the calculations manually is a major pain in the butt. But I am going to now take something else into account. We said there should be an effect from each A. There should be an effect from each B. But now I think there might be some combined effect because I have multiple pieces of data within A, J, B, K. That one thing might have some variation within it. So here we get an extra interaction idea. Somehow, the fact that I'm going with this driver to this hotel might make a difference if I took multiple readings on that one person. So I'm going to do the same sort of process. I'm going to say how much of the variation is due to my choice of A, how much of my variation is due to my choice of B, and how much of my variation is within the one box containing that data. So here is an example of such a set of data. Problem number 27. This is just the summary data. Let's pull the problem itself. The problem says, a market research firm is testing consumer reaction to a new shampoo on 4 age groups in 4 different areas of the country. There are 5 consumers on each panel. Each consumer gives a 1 to 5 rating and a 10-question questionnaire. Average score is what's written down. And so by age in the rows, by region across the top, what do they think of the shampoo? Does your age change your opinion? Does your region of the country change your opinion? Within one of these boxes, how much does the variation within that box affect the average for that particular group? So 3 different kinds of effects. Main effect for the row, main effect for the column, and within the box, the interactive effect. Now, I can just run the ANOVA. But in and of itself, I'm not sure that helps me all that much. So let me pull up the Excel sheet, number 27. That's number 25. This one's number 27. There are my data sets. And when I do the same ANOVA that we were doing before, data analysis, this time I use with replication because I have more than one data point per box. And when I go to set that up, notice there's an extra line here. It says, give me the input range. And then it asks, how many rows per sample? In this case, there are 5 people on each panel, so I got to change that number to be 5. Then it'll spit out the same data. So input range, click. I need to make sure I get the top row. Well, let's take off the labels. We'll just do the data itself. There. Rows per sample is 5. I'm doing an alpha 0.05 again. This is a 95% confidence interval, 5% sensitivity. Give me my output. Each sample must contain the same number of rows. What did I screw up? With replication. Try again. Group. Five rows per sample. Oh, maybe it insists that I have the titles. So let's include the titles. I do it that way. Go. That's the way I do it. I need to include the titles. I apologize. This doesn't look like very much at first. I blow it up so it's readable. And now there's a whole lot more information up here in my summary, isn't there? Notice what it's given me is it's given me a grid of the same kind of data. So this first box here, that's the Northeast Youth Group. And in my Excel spreadsheet, that first set of information is the Northeast Youth Group. Notice there's a variance for just that group. So it computed variance within that one group as well. For all of these. And then per the entire row, right? So there's a row totals on the end. And down here, there are column totals as well. So that's everything for the Northeast. Underneath all of that, here's where it does the F calculations. So this is the information I want right there. And for the most part, I really only want the last 3 columns. But I need to know which one goes with which. So that first one says sample, that's the rows. The next one says columns, and the third one says interaction. And so I can ask 2 questions. My hypotheses. I need to know what my hypotheses are. This is ANOVA. I'm checking to see if the variation changes. So my null hypothesis is that there's no effect due to row, there's no effect due to column, there's no effect due to interaction. All my averages should be the same regardless of which row, column, or box we pick. There shouldn't be any variation. The status quo is everything is okay. The alternate hypothesis, something is different somewhere. Now I can say, okay, do the rows have an effect? Rows is the first set here, first set of numbers. Do the rows have an effect? How do I answer that based on the information sitting here? I can look at the p-value, absolutely. If I look at the p-value and the p-value is sufficiently small, then I'm out at the edges and I should reject. So the p-value for this, oh boy, 5.56. Now a lot of people read that and didn't read to the end of the number. What's that E minus 14 mean? How many zeros in front? So that's 0.00000000000005. Is that smaller than 5%? A hell of a lot smaller than 5%. So I should reject. The row does have an effect. Row goes with which piece of data? That's what it says there. It says sample, right? But that's age group. Okay. Does the column have an effect? Why not? P-value is 0.64. That's a lot bigger than 0.05. I should not reject. And that means that my column was region. Geographically, where I am doesn't affect my opinion. Northeast, Southeast, Midwest, West, doesn't matter. People in every part of the country roughly think the same, but by age, they think differently. Interaction effect. Is there a particular group where age and location seem to cause more variation or less variation? My null hypothesis is no. There should be no interaction there. Fi, the interaction level, that third row there, is there an interaction effect? Why? P is 0.0009. That's way less than 0.05. I should reject the null. There's some. I don't know which one yet, but there's at least one group where age and geographic location matter and cause more variation among that group than others. And this is the downside to an ANOVA. I don't know which interaction is prevalent. I know that there is an interaction. I just don't know what it is. So how could I figure out what's going on? Please notice the fact that the p-value for age, the rows, is so tiny. The fact that F calculated is 37 and F critical is 2.7, we're way out there. Age makes a huge difference here. But the F value for the interaction is only 3.6 and the critical is 2.0. So there's a little bit more than would be needed to say there is an interaction effect. Okay. Let me go back to this summary data for a minute. We just said that columns don't make a difference. So if I were to plot each row, I would expect parallel behavior. I'm going to do that. I'm going to take the averages within each row and I'm going to plot those as line charts. I'm going to take the average of each column and I'm going to plot those as line charts. So here, this is across each row. See how they cross each other a bunch? That's a high degree of interaction. Here, there's very little interaction. A lot of those go the same way, don't they? So that's across, that's by region, that's down each column. If the interaction is high, plots cross each other a lot. If the interaction is low, plots cross each other a little. If the curves are further apart, like there are bigger differences, then that factor has a lot of impact. Those are very close together, aren't they? So by region, didn't matter a lot. Those are very tightly grouped. But by age, across the regions, there's more spread in those lines, isn't there? And so if I notice, hey, plotting by age, notice each column is a region, across the regions, by age, that makes a difference. It's spread out more. Age matters more than location does. Now, I would say it would be nicer if I could get more precise data. If I go back and look at the data that we were given, the original data, these are only two significant digits, right? This is not a very detailed scale. And so my result is rather coarse. It's not a very deeply detailed result. But notice what I can answer. I can say the factor that makes the most difference one with a teeny tiny p-value with a huge F calculation. That is age. So now I can say, okay, who should I market to? What age is the appropriate target for this shampoo? Now again, each individual product, each individual line that I'm working with, whatever it is going to give me the opportunity to figure out what's an important affecting idea here. Questions? Four distinct stock portfolios. And each portfolio has 5 stocks, volatility coefficients. Wait a minute, volatility coefficient? What's a volatility coefficient? Oh, we did that. That's coefficient of variation. I remember that back in chapter 4 in our descriptive statistics. So they plot the coefficient of variation for each one. The question is, does year matter more or less than portfolio sector? The sector matter more than year? Is there more interaction? Is there one year where one particular portfolio type did much better than the others? Or is it pick one and stick with that? Again, I'm looking at 3 different effects. Does year matter? Does sector matter? Does interactivity matter? What are my null hypotheses? My alternate hypotheses? What am I going to test?
The null is that they don't matter.
The null is that every effect is 0. That which column you're in doesn't matter, which row you're in doesn't matter, and there's no interaction between row and column. All of the effects are 0. Therefore, the alternate is at least one effect isn't 0. I run my ANOVA. There's all my summary information by year, by column, sector, and way down here at the bottom, is my summary data from the ANOVA itself. So, first question. Does year matter? Why? F for year is the rows, is 67, F critical is 3.2. Or p-value has a 10 to the negative 14th in it. That's a lot of zeros in front. That's a really, really, really small p. We must be way out there on the integral, on the curve. Okay, row matters a lot. column? Does sector, type of portfolio matter? Because
It's not as big of a difference.
right. F calculated is 5.5. F critical is 2.8. It's bigger. We reject. P-value is 0.002. Smaller than 0.05. Small p-value, unlikely to have happened randomly. There must be some connection here. Interaction. Same call again. F calculated 4.96. F critical 2.3. P-value 0.0005. Too many zeros, it's too small, we're out there. Again, I can create interaction charts. There were 3 different years. And I look at the top graph 2018. 2018 was a better year than 2017. 2017 is the blue year, 2018 is the red year. Red's on top by substantial margin, right? But those almost exactly keep pace with each other, don't they? There is some interaction here. 2019, one sector went up more than the others. So there's some interaction between year and sector. And if I switch the arrangements, again, I see one major crossing. But it's clear that year, there's a big difference in year, isn't there? There's a lot more variation in 2019 than there was in 2017 or 2018. 17 and 18 are fairly close together. 19 is fairly far apart, isn't it? So these interaction plots help me track down what pieces mattered how. If I wanted to get a closer understanding of how these two things affected each other, I could do 12 different pairwise t-tests. I could say, take the data from 2017 from the health sector and tell me what the variation was. And then I could compare that variation pairwise to 2017 in the energy sector. There's a number of other interaction tests we can do. Excel does not perform those calculations automatically. Several other statistical analysis softwares do. So if you're looking for such a thing, there's one that is called a Tukey, T-U-K-E-Y, a Tukey test, that allows you to test individually across different groups for the particular variation. I think that's beyond the scope of what I want to talk about here. But this sort of visual isn't automatically generated, which is why we need to be able to generate the line plots, the bar plots we did back in chapter 2. It was a long time ago, man. But this is the critical piece of an ANOVA. Reading this table. Notice what is 100% missing from every result in Excel. The ones you saw on the exam, the ones you did on homework problems, the ones we did here last week and this week. You know what's missing? Say again? Variances in there. I've got variances up here within each row, within each column, within each group. I've got variances. there's no real discussion of what the error is, right? I don't know what bias might exist, what sampling error I could have. There is no discussion of error. We'll have to figure that one out, right? What else is missing? Hypotheses. Doesn't tell you what question has been answered. You have to provide that. And that's why in every ANOVA that we've been doing, the question has been, is there no effect? Is there an effect? The two-tail test. ANOVA. In the t-tests and the z-tests, all of that was ones where we had to decide which question were we asking. Once we decided which question we were asking, this would tell me the answer. But I need to know what the question is first. Anybody watch or read or know Hitchhiker's Guide to the Galaxy? I feel so old, I apologize. Hitchhiker's Guide to the Galaxy is a Douglas Adams series of novels, very surreal, very bizarre pieces of science fiction. It was a radio play, a TV miniseries, and a movie, and a lot of other things. The very beginning of the first book in the series opens with the destruction of the Earth, which pisses off a lot of people. It turns out that the Earth is an organic computation device because on a distant planet far away, a bunch of scientists got together and asked a great artificial intelligence computer, what is the meaning of life? What is the purpose? And the computer answered, 42. Doesn't make any sense. That's right, it doesn't, because you don't know the question. And so they built the Earth to answer the question. And so they're spending the rest of the series of books trying to recover enough information from the Earth to figure out what the question was. I can do all the statistics till the cows come home. Doesn't mean anything until I know the question I'm trying to answer. I can ask one other thing that isn't up here. Can I predict the result of a new portfolio? What's written up here is information about these four different sectors from 17, 18, and 19. Could you make an estimate for what you think is going to happen in 2020 for each of these? Could you kind of try and figure out, well, health has these stocks in it, energy has these stocks in it. What if I made a new category? Health, energy, retail, leisure, environmentalism. What if I made environmentalism and I picked these 5 stocks? How would it compare? How can I use these sorts of ideas to do predictive work, not just descriptive and inferential work? Doing that is one of the groundbreaking pieces in modern data analytics. The fact that we can make all these calculations happen so fast. By the way, the first time I did this problem, not this one in particular, but an ANOVA problem like this, I was roughly your age, and therefore my computer lived in another building and I had a dumb terminal in front of me. And most of the time when I went to interact with it, I had to bring a stack of punch cards and come back the next day for the information. Me doing this problem took 3 hours overnight. It took us 12 seconds. So what if I had not 5 pieces of data over 3 years, but 5,000 pieces of data per source over 30 years? What prediction analysis could I make? You are sitting on a goldmine of information. Can you ask the question that data will allow us to answer? Questions? What do you have for me right now? I need a question. Whether you think a question you've got or you think it's a question somebody else has that they're too chicken to ask. Somebody ask me something. If that information is still making you unhappy, you should come talk to me. If that information is making you distressed and you're going to spend your Thanksgiving being nervous and upset, don't bother. Trust me, everybody in this room is passing. You are all doing okay. If you don't like what you got, you'll see questions like it again. You can restudy them and do better. I have full faith that you are all capable of that. But I am going to do you a Thanksgiving blessing, and I'm going to let you get out of here. So I will see you all in a week. Have a wonderful break. If you came in late and I still have your exam, come get it from me. Otherwise, enjoy your holiday.